Okay, so this is the third lecture by Mateusz, and so please, let's get started.
Good morning, good afternoon. Actually, it's afternoon for everyone. No, morning for US people. So I finished last lecture by promising that we will start to join the construction of line bundle and vector bundles, K-theory, and the Churn. So in particular, our first step will be to start with line bundles. And cook up from it codimension 1 subvariety of X. Okay, that's our first aim. Now, the group of isomorphism classes of line bundles, this is known as the Picard group. Now, if you know a different definition, this is also the group of Cartier divisors. If you know a different definition of a Cartier divisor, it is a very good way, it is a very good small exercise to convince yourself that the definition you know is exactly the definition that you need to reconstruct a line bundle using our definition. Okay, so what happens when we have a line bundle? Well, we know that locally on some open set U1 of X, this line bundle has a trivialization. So L restricted to U1 is isomorphic to C times U1. And this means that although there are no global sections, we always have a rational section. There is always a rational section. A non-zero rational section. So let me say what I mean by this. By this, I mean a map from X to the total space of the line bundle that satisfies the condition of a section, so that if we compose it with projection, we get back the identity. But this does not have to be defined everywhere. So I allow it to be only, if it's fine if it's only defined on a Zariski open set. And in particular, I can define it on U1. Why? Because on U1, it does make sense to send it to U1 times C, just sending a point to a point times 1. Okay? So on a trivialization, when I fix a trivialization, 1 makes sense. It does not make sense to speak about 1 in a fiber of a line bundle, but once I fix a trivialization, it always makes sense. Okay, so we will use this section to define a divisor. So this is a section, I will call it S, and we define D of S. This is the sum of subvarieties of codimension 1 subvarieties of X. So this is codimension 1. And now we take the order of our section S at order at Y of our section S, and we take the class of Y. Yeah. Okay. So what do I mean by the order of a section? There is something in chat. Line bundles with tensor product. Yes, Alessio here makes a comment. What do I mean by pick X as a group? There is a tensor product of line bundles. Okay, so now what do I mean by an order of a section at a variety? So either this section has zeros at the codimension 1 subvariety, and then this is a positive integer that stays there. This is the order of vanishing, or it has a pole. And if you would like to understand poles in terms of zeros, then just take 1 over S. 1 over S will have then zeros at Y, and you take the order of zeros. Now, I will now make an example. So I'm going to pass to a new slide. How to do this with O of -1. Okay, so you will see this order of vanishing on in the case of the line bundle O of -1 on P1. Okay, so example, I take the variety P1. Yeah, this is the projectivization of a two-dimensional vector space, and I take the line bundle to be O of -1. Okay, now we know how to trivialize this. This was already an example from the previous lectures. So recall that there is an open set that consists of points 1x. Yeah, this is an open set on P1, and on that we have a trivialization of U1 times C. Well, first we can map it. So let's say that this is the projectivization of a two-dimensional vector space V. So we can map it to U1 times V very explicitly. We are sending 1, 1x, a point here, and a number t to 1x and a point on that line that corresponds to t. So we just multiply by t. So that's t comma tx. Okay. Yeah, this is the trivialization of O of -1. The image lands in O of -1. Okay. If there are any questions about that, please ask. And on this, we can consider a rational section. Rational section. Well, very explicitly, what kind of rational section? Well, we send a point 1x to we have to send it to a line bundle restricted to U1. So only the part that lies above U1. This is inside U1 times V. And where do we send 1x? Well, we send it to 1x, 1x. Okay. Is this fine? Okay, so in particular, notice that on U1, this section has neither poles nor zeros. Yeah, because 1x is never a zero and it's always well defined. Okay. Yeah, this is what would correspond to the section 1 that I said on U1. But then there is another open set. There is an open set U2. Maybe I will write about U2 here, which is given by, well, the other affine piece, that's x1. Okay, inside P1. Okay, so let's see how this section looks on U2. So first we need to understand the trivialization. The trivialization is very similar. So now we will have U2 times C to U2 times V, and we will be sending x1 comma t to x1 comma txt. Okay, this is the trivialization on the other piece, and well, our aim is to understand what our section induces. It will be a rational map on U2. Yeah. Okay. So here we go to our trivialization, and then we project to C. This will be a rational function on U2, and we would like to understand it. Where do we send x1? Well, let's say that x is non-zero. Okay, so let's assume that x is non-zero. So then x1 is equal to 1 over x. Okay. And we know what our section does on such things. Okay, we picked here a rational section. Well, it sends it to, of course, it does not change the base point, and as a point of V, So I will now write a point in, this will be a point in the intersection of U1 intersected U2 times V. And the point of V is just 1, 1 over X. Okay. Okay. So now we notice that under the trivialization map, how do we get this point? What value of C we have to take to get this point? Well, so I claim that we need to take x1, 1 over x in u2 times c. Okay, so if we take this point in u2 times c, then it will exactly map to this point here. Okay, this point maps here. Okay, so I'm just telling you how this section goes here. It sends a point x1, 1x to the same point, but 1 over x. x1, 1 over x. Okay. Okay. So I use the other chart to see that. And then there is just a projection. There is 1 over x. Okay. So on this other chart, on a point x1, I'm getting 1 over x. Okay. That's how my function looks in the other trivialization. And 1 over x has a simple pole, has pole of order 1, at well, the unique point that is u2 minus u1. Okay, the point corresponding to x equals 0 in u2. Okay, so this means that d of our section is minus a point. Okay, we only have one point on which our section is either 0 or a pole, and it happens to be a pole of order 1. That's why, so this minus is really -1, which comes from the fact that this is x to -1. Okay, I will maybe make the -1 red. Okay, so actually, you may say that I cheated here because come on, algebraic geometry is not only about studying univariate polynomials, and everyone knows what is the order of vanishing of a univariate polynomial or a rational function at 0. What happens if we have any function in any ring, and what is this order of vanishing? Okay. So the good news is that we have assumed that X is smooth. Without that, the definition is not so easy, which means that if you localize your ring at Y, so if you look locally in the neighborhood of X, so let's say this is an open neighborhood of spec R, and if you localize your R at the prime ideal of Y, this happens to be a regular one-dimensional ring. And for regular one-dimensional rings, they are DVRs, discrete valuation rings. And in other words, this means that that you can check, and it behaves well, to which power of the maximal ideal S belongs. So if you want to know the order of zeros, then your section will be a function. It will be an element of that ring, and you just check to which power of the maximal, the unique maximal ideal after localization it belongs. But it's not more complicated than we did it in the case of P1. There is a question. So there is a question if the section I have chosen does not have a 0 in U1 minus U2. So let's see. Let me go back. So the section on U1 is like that. Okay, no, sorry, it's I circled the wrong thing. It's like that. So notice, well, this is just the point on the variety, and the important thing is this. This is never 0. 1 comma x is never 0. This section does not have a 0, even if x is equal to 0. 1 comma x is not a 0 point on your line. Does this help? Let me see. Ah, okay. Oh, I see. That's a very good reaction. Okay. Okay. So altogether, the theorem that I want to tell you, and it's also a definition, is that the map that associates to L ds descends. So first of all, this is not a function because I made a choice of a section, yeah, but it descends to a map from the Picard group of X to A1 of X. Okay, so in other words, if you change a choice of a section, you do change the S, but you do not change the class in A1 of X. Okay, is this fine? Okay, I see no questions, so I'm going to the next slide. Now this map C1 in general, when X is not smooth, it does not have to be injective or surjective. I think this is very surprising because I always think that this is an isomorphism, and it is an isomorphism when X is smooth. So actually, it's if you want to know, it's for locally factorial varieties. So those that locally are spectra of UFDs. Okay, so C1 is so C1 of L is the first Churn class. Churn class of a line bundle. Okay, and we will also say that higher Churn classes vanish. Let me put it in general. If E is a vector bundle of rank R, then the kth Churn class of E is 0 for k greater than R. So for line bundles, well, there is also the 0th class, which we will always set to 1. So for line bundles, you now know all the Churn classes. The 0th is 1. The first Churn class is the divisor that I have just described, or the class of that divisor, and highers are 0. Okay, so our next step is to define Ci of E, where this I is now from 1 to R for arbitrary vector bundle. And there are many ways to do that, and I will describe two. One will be informal, but helpful in actual computations, and the other one will be very formal, but well, sometimes also helpful. I will not say not helpful, but maybe less intuitive. So I first do the intuition. Okay, so what happens when C1 of L happens to be 0? Yeah, what does it mean? Well, it means we have chosen a section that has neither zeros nor poles. Okay, S, global non-vanishing section. Non-vanishing section. Okay, and I told you that vector bundles or line bundles are not always trivial because we don't know where is 1. But if you have a global non-vanishing section, it can tell you where is 1. Yeah, so then you can build an isomorphism with this, just by sending one, you send x1 to x and s of 1 to, well, or s of x, sorry, s of x formally. Okay, that makes sense because this section is well defined and non-vanishing. Yeah, and you extend so if you don't have a 1 here by t, you just have to keep the point x of x, but multiply by t the fiber. Okay, so somehow the first Churn class tells us how much we failed to trivialize line bundle L. So say that now we want to trivialize E. Well, if it is of rank R, we want R sections. We want S1 up to SR sections that are linearly independent in each fiber. Okay, so notice that then we can take S1 wedge SR, and this will be a section of wedge RE. Sorry, let me check. So the first Churn class is a measure of how much we fail to trivialize the given line bundle. Yes, in some sense, yes. Actually, I think they were designed to that, to distinguish from trivial, to have an invariant that distinguishes from trivial. Okay, and now again for vector bundles, exactly the same. This will be a measure how much we fail when they become linearly dependent. So we define C1 of E by definition to be C1 of wedge R of E. Okay, this is now a line bundle. And again, in some sense, it's a measure how much we failed, but be careful. The fact that this is 0 does not mean that this is trivial, because we might not have sections S1 up to SR, global sections, and that's one of the problems. So remember, this is just an intuitive definition. I mean, this is a formal definition, but the intuition with global sections needs some assumptions, like, for example, the existence of global sections. Okay, so in general, we will proceed quite similarly. So we choose S1 up to SR minus E plus 1, general global sections. General global sections. Okay, and we set the set, we look at the subset of X, which consists of those points of the variety where these sections, yeah, so if we evaluate them, we are getting a point in the same vector space. So SR minus I plus 1 of X, they fail to be linearly independent. Fail to be linearly independent. Okay, so at some X it could happen, at some X it could not happen, but the assumption that we will make, codimension of D is equal to I. And if you do the dimension count, that takes some time, but is quite trivial, you will see that this is what you expect. So if you would think about them locally as functions, this is what you would expect, that the codimension of the set D is I. And in that case, we have a very straightforward definition of Ci of E. Well, this is just the sum of components of the variety of classes of varieties of components of D. Sum of classes of components of D. So in some sense, the ith Churn class tells us not when we take R sections, but just when we take less sections, they may still fail to be linearly dependent, and how much they fail tells us the ith Churn class. And okay, so maybe let's go back to line bundles for a second. How would what would this definition tell us for line bundles? So when we want R is equal to 1, if we want the first Churn class, we just take a general global section. And there are two things that could happen. If we have global sections, this will be exactly our rational S. Or I mean, well, if we have a global section, it's not even a rational, it's everywhere defined. And our construction coincides with the previous one. But it could be that we don't have global sections, or in other words, that 0 is the unique global section. Then 0 happens to be linearly independent with itself nowhere, because it's everywhere 0. So it's everywhere linearly dependent. So D is the whole variety, and in particular, it does not have codimension 1. Yeah. For this reason, we cannot use the 0 section to define the Churn class of a line bundle. We have to use another section. Okay, so this is the intuition, and now we come to a more formal definition of Churn classes of line bundles. But please be aware that in a lot of computations, this is what actually you have to do. You have to take classes, you have to take sections, and see where they become dependent. Okay, so now another definition for projectivization of line bundle. Okay, sorry, not line, of vector bundle. What did I write? I wrote I mean projectivization of vector bundle. Okay, so there is a question. Yeah, so I want them to be general global sections, and I'm somehow assuming they exist in particular. So when you don't have global sections, one has to be very careful with these multiplicities, and it's very easy to arise at false conclusions. So it's better to assume that you really have general global sections. Okay. So if we have a vector bundle over X, vector bundle, there is another variety associated to it, which is its projectivization. So if you've seen this construction, that's good. If not, it just replaces the, so here over X, we had the vector space Vx, and here we will have the projectivization of that vector space. And if you want to do this really formally, you have to take the trivializations. You need to projectivize there. So there you will just have a product of UI and the projective space, and you have to use the transition functions to glue those pieces together. This will glue together well. And the advantage is that this variety comes with a line bundle. Comes with a line bundle. O of -1. And how to construct it? Well, over a point here, P, well, it's the line corresponding to that point in this projective space. Okay, this is a slightly informal definition, but I think it gives a good flavor. It's just a globalization of the construction of O of -1 we have seen for a projective space. It's just that now this projective spaces also vary. Okay. So let me call this projection pi, and now I can give a very formal definition of Segre classes. So the ith Segre class is the push forward to X of what? Well, I can take the class of O of 1 upstairs. So O of 1 is just dual, it's a line bundle dual to O of -1. And C1, you should think about this as taking a hyperplane in every single fiber. Okay, so we the C1 of O of 1, you should imagine a hyperplane in over every X in every single projective space. So it wouldn't make much sense to push it forward because that changes the dimension. And in order for it to not change the dimension, we need to intersect at least R minus 1. So the rank of E is R. We need to intersect these hyperplanes at least R minus 1 times. We may intersect them more times. So I will put a plus I here. And then if we intersect them more times, in general, what will happen, we will get an empty intersection. But over some special points of X, it could happen that this still intersects, and that's our definition. You can check that this lives in AI of X. Okay, so this is the Segre class. What it has with Churn classes to do in a second, just a notion. So Segre classes, I define it for any I, and in particular, this can go beyond the rank of the vector bundle. I'm not saying they vanish beyond the rank of the vector bundle. In fact, in many cases, they do not. So now a formal theorem. There exist unique Ci of E in AIX, the Churn classes, such that 1 plus S1 of ET plus S2 of ET square plus and so on times 1 plus C1 of ET plus C2 of ET square plus and so on. This we want to be equal to 1. Where is this as an element of what? Well, it's an element of A of X, and there is this new variable T that I just use. So these are polynomials in T that I just use to for convention. So notice that this is just an easy way of writing it. You could also make this product out, and this will tell you that the coefficient of T is just S1 of E plus C1 of E. So you can write it explicitly that, for example, C1 of E is minus S1 of E. If you want C2 of E, well, if you do the product, you will find out that this is S1 of E squared minus S2 of E. Okay, and the Segre classes were already defined. In any case, the general formula for the nth Churn class using the previous one and the Segre classes is minus S1 of EC and minus 1 of E, and then well, the Segre classes indices grow, the Churn classes indices go down. This is a really easy exercise if you want to do it. It's just basic algebra on the polynomial I have written above. And by convention, we also say C0 of E is equal to S0 of E is equal to 1. Okay. So that's yet another, well, this is a very formal definition of Churn classes. It does not really say a lot what they are, but yeah. Okay. So now more things. So okay. Now notice that this morphism by the pullback, it makes by pullback, it makes this Churn this Chow ring a module over A of X. And the theorem is that this is a free module generated by I will let me write it just just xi to the I for I from 0 to r minus 1, where xi, well, this is the first Churn class of O of 1. Okay. So if you look to Hartshorne, he will yet differently define the Churn classes, because this theorem tells you that xi of r, xi to the power r, well, it can be uniquely, this stops at r minus 1, this can be uniquely expressed with coefficients from ax as sum of powers of xi i's. So in other words, we need to have a formula of the form as follows, where I is summed up from 0 to r minus 1 for some xi that are in the chowring of x. Okay. Well, the fact that they are in the chowring just follows from the fact that this module is generated by those things, and the fact that they need to be there, it just follows by the degree count. Okay.
Mateusz?
So yes.
So this thing is a module over AX, and you're basically saying that you just need the powers up to, well, r minus 1, I guess, to
Yes.
generate those, and they're also free. Does it say something on the, I mean, I guess that since it's a chowring, it would also have a ring structure.
Yes.
But would you get something like Q, no, I don't know, the K of xi over that relation you've just written or something like that? I mean, is there any reflection on the ring structure?
So notice that this relation exactly tells you the ring structure, because it tells you how to multiply by xi once you, so you know, if you start from
Wait, something weird happened to your audio.
Hello, can you hear me?
Yeah.
Oh, okay, sorry. Somehow my Zoom told me that the microphone changed. So notice that on this part, as long as you are in this range, multiplying by xi is trivial, because if you take xi to the 5, if you multiply it by xi, you just get xi to the 6, a new basis vector. And this relation tells you how to go further. So if you multiply the last basis vector by xi, you need to get other things back. Yeah.
Okay, but so these
and
actually
this relation tells you how to do it. Of course, you can multiply it further by xi, and then from this relation you can read off what are these further powers, how to present them in the basis. So from this you can, for example, compute xi to any power, the multiplicative structure.
Okay, but then the theorem is stronger than what I would have thought if you just told me it's a free module. I mean, it's a free module, but you actually know the whole ring structure. That was my point. I just meant that.
Yeah. So, but the ring structure you only know a posteriori, if you know. So I haven't told you yet what are these xi's. So you have to know this, yeah. What are this for some xi's? I mean, this does not tell you a lot. So now let me tell you what are these xi's.
Okay, thanks.
Well, these are exactly the Churn classes, and this is how Hartshorne will define them. So these are xi is just the c dimension of x minus I Churn class of E. Okay. Okay.
Mm-hmm.
And some people will define it this way. They will tell you decompose xr in the basis, and the coefficients you get are Churn classes. Okay. Oh, sorry. I think I should have r minus I here. Okay. So the proof that these two definitions are equal, I basically do it in the notes. So it relies on a projection formula that is in the notes, and I will also discuss it in details tomorrow. But if you know projection formula, well, I can also write it to you. It tells you that if you push forward a pullback of anything, times B, then this is the same as taking the product of A with the push forward of B, and this projection formula. We will also see it tomorrow. Okay, so if you use it, I spent more details on this in the note. You can see that the two definitions I have given are equivalent. Okay, so this is the definition of the Churn classes and of Segre classes, a very, very important topic in enumerative geometry and in topology, in algebraic geometry, and so on and so on. Now, once we know the Churn classes, there are a few related definitions. There is the Churn polynomial, which encodes all of the Churn classes in the same time. We already seen it when we were looking at the definition of Churn classes from the Segre classes. This is defined as follows, and this is in AX of T. Okay, so it just keeps the ith Churn class next to T to the I, and then there is the total Churn class, which is just the sum of all of them. Okay, so this is denoted by C of E, and this is just the sum of C of E. Notice, so this does not look like a polynomial because the sum is infinite, but remember that the CI's vanish above the rank, okay? Above the rank of E, so this is really a finite sum. Yeah, and this is in A of X. Okay, so these two things encode basically exactly the same thing, but they are very useful for computations, and I will just tell you one theorem that allows you to compute all Churn classes very quickly if you have exact sequence. So let 0, V1, V2, V3, 0 be an exact sequence of vector bundles, then the Churn polynomial of the middle one is the product of the Churn polynomials of the outer ones. Okay, so this is a really convenient way to compute Churn classes. Okay, now in particular, corollary, if V is a sum of line bundles, so this is not always. Some vector bundles of rank R are not sums of R line bundles, but if this happens, then the Churn polynomial of V is equal to the product of 1 plus, well, this easy first Churn class of Li. The product is from 1 to RT. Okay, and this is just you use this inductively for the very easy exact sequences when you split off one Li at the time. Okay, now it is not true that we can always write this, but there is in fact a theorem known as the splitting principle that tells us more or less that whatever equality and whatever you want to prove about Churn classes of a vector bundle, you may assume that this vector bundle is a sum of line bundles. And the trick is to introduce Churn roots. So I will do it in the second half. Just let me make an appetizer. So we will pretend that Ct of E factors. And how to make it more formal, let's see after the break. So thank you for the first part. Of course, I'm happy to answer any questions there are.
Okay, so are there any questions on the first half? I would have one. So
Yes.
what is the intuition behind a vector bundle being a sum of line bundles? Like when it actually does happen, what does it mean? What should I know about the vector bundle? I'm not sure it makes sense, but is there anything I should be reminded of?
Well, there are many conjectures that this happens a lot, especially for low rank vector bundles on projective space. Basically, that it happens always, but of course it doesn't happen like always when you allow arbitrary rank. Yeah, so things like tangent bundle are examples of things that do not split. But I would say this is somehow considered the simplest case. This is what happens in a lot of branches of mathematics. If you want to understand an object, you try to break it into simpler objects. You try to write it as a sum of simpler things. And you can do this in representation theory, and then you focus on irreducible representations. You can do it in group theory, basically everywhere. Even in algebraic geometry, you focus on irreducible varieties. And I would say that once your vector bundle is a sum of two vector bundles, everyone will tell you to study those two things separately. So if your vector bundle is a sum of line bundles, then you just have to basically well understand the line bundles. I don't know if this is a satisfactory question.
No, it is. I mean, I kind of understood the principle. I guess I thought there was a geometric explanation that happens. I guess it's not really there from what you've just said.
Well, I wouldn't say it's like very easy to say. As said, I think it's an open problem to prove,
I mean,
for example, that vector bundles.
That's already kind of an answer, I guess.
Yes, so it's not a trivial property, but it's like somehow a wanted property.
Okay, are there any more questions? Okay, if not, I guess we take 10 minutes on the recording, please. Okay, we start with the second half.
Hello, so welcome to part 2. So I promised you that we will pretend that Ct of E factors, so let's pretend. Well, if it factors, it's something like this. Yeah, this is a degree R polynomial. So we have a product from I equal 1 to R. Now, what are AIs? Well, I told you that if E splits, these are just the first Churn classes of the line bundles. But in general, AIs do not make sense. They are nothing. They are just formal expressions. Yeah, they are called Churn roots, but we don't think about them. I mean, you can think about them as classes in the Chow ring, but they don't have to be classes in the Chow ring. So what actually only makes sense are elementary symmetric polynomials in AIs. Why do they make sense? Because they are the Churn classes. So very explicitly, the kth elementary symmetric polynomial in E1 up to ER, this is the kth Churn class of E. Or even more explicitly, the first elementary symmetric polynomial in A1 up to AK. I hope that by one, everyone knows that this is just a sum of A1 up to AK. Well, this is the first Churn class of E, and so on and so on. So A1 does not make sense. Only if you add all the A's, it makes sense. It is an element of the Chow ring. Okay. So why do I introduce objects, churn roots that don't make sense? Well, because they are very handy tools to compute churn classes. They are great to compute churn classes, and in what sense they are equal? So they are great. So let me tell you that under the operations, basic operations, it is easy to say how churn roots change. So let EF be vector bundles with churn roots. So I should have probably written here that these are called churn roots. Churn roots. Yeah. So again, it does not make sense to ask what is the first churn root. You can only ask about elementary symmetric polynomials in the churn roots. So if they are vector bundles with churn roots, okay, maybe I will write it like here. So this has AIs, this has BJs. Yeah, everyone has its own rank. Then we know the churn roots of many other vector bundles. So fact, the roots of E dual are, well, you just negate the roots of E. The tensor product, you just add any I to any j. Yeah. So notice that in particular, you always have to have rank many. And here you have like R rank of E choices for I and rank of F choices for F. Okay. Is it clear what I mean by this? That E tensor F has AI plus BJ? Maybe someone wants to oppose. What do you mean? It's not a complete sentence, or otherwise I will continue. Okay. So then wedge P of E. So the churn roots are AI1 plus AIP, where you have to take an strictly increasing sequence of indices of churn roots. If you take the symmetric power, then AI1 plus AIP the same, but now you just take weakly increasing. Okay, so in particular, they may be equal. So I decided to do this by example. So of course, many of you solved yesterday's problem of deciding what is wedge to O of -1 to +2 using exact sequences. I know because a lot of people reported this to me. But let me show you how to do this using churn roots. So recall that we are on P2, and well, let me call C1 O of -1, let me call it by -x. Yeah, this is a line bundle and it has just one churn root. Okay. So O of -1, sorry, any questions? To 2. Okay, so maybe let me ask you a question. First, how many churn roots will this have? I'm not asking what are they, but how many? Anyone? 5 minus 3, pi divided by 2. Come on, anyone. How many churn roots this will have?
Should be 2.
2. It should have 2 churn roots. Okay. Now, can anyone say what are these churn roots? If we know the churn roots here, it's -x. Well, we would have to build an exact sequence, and remember that the churn polynomial of the middle thing multiplies. So in particular, if you know churn roots of the left thing and the right thing, then you just take the multiset of those churn roots together. Yeah, and we know of O of -1. So this will have -x and -x. Okay. Now, if we do wedge 2 of O of -1 to the second direct sum, well, we have to take distinct churn roots and sum them up. Yeah, this was This was this one. Yeah, we have to take two distinct indices. Well, if there are two indices, then the only thing is to take them distinct. So this has one Churn roots minus 2x. Okay. But also O of minus 2 has just one Churn roots, and this is minus 2x. Yeah. For example, from the tensor product construction, because we have to add minus x to minus x. So it means that the Churn roots of those two things are the same, but we know that every line bundle on P2 is of the type O of A. So in fact, the first Churn class determines it. Yeah. So those two things are equal. You can also see it this way. Any questions about that? I'm going to the new slide.
Sorry, so like what you needed to conclude was the fact that you know the structure of line bundles on Pn.
Well, maybe I even
yeah.
didn't need that, because I also, well, okay, if I want to just speak about classes in K-theory, I'm safe. I even don't need that. Yeah.
So you mean that if you have this kind of equality of Churn roots for two different bundles, you know that they must coincide in the K-theoretic
Well,
sense?
I told you that C1 is an isomorphism of peak X to A1 of X, and P2 is smooth. Okay.
Mm-hmm.
So if C1 agrees, the line bundles have to be
very nice. Okay.
The same. Okay. Yeah. So not even in K-theory. Yeah. Okay.
Thanks.
Okay. So let me continue with a slightly more complicated example. But the good news is that you already did that more complicated example. So now we do the Grassmannian GRV, where the dimension of V is n. And well, we have the trivial vector bundle. Now, maybe that's again a good question for you. What's the Churn polynomial for the trivial vector bundle? So remember, if something splits, the Churn polynomial is just a product. Yeah, and trivial things tend to split. So anyone wants to make a guess? Oh, there is a guess. Let me check it. 2, 1, 1, 1. Yes. 2 was probably the answer to the previous question when I was asking. Sorry, I have to turn on one thing. My computer. Really sorry for that. Okay.
Wait, Mateusz.
Your microphone is not working anymore.
Yeah.
Hello, can you hear me?
Now
let's try to do this for something. Oh, sorry. Did I break for a second?
Yeah, for like, well, 10 seconds or so, I don't know.
Oh, sorry. Can you hear me now? I'm really sorry.
No, it's fine.
Hello. Okay. So now our aim is to compute this. So remember that the Grassmannian also comes with a rank R universal bundle and a dual to that. Okay. But the good news is that we know sections of that. Yeah. And think that this, what we are doing right now, is not very different when I was trying to tell you what happens to O of -1 or O of 1 on P1. But now we have to use the intuitive definition. We need to take global sections. And the question we have to ask is like, when E1 dual, ER minus I plus 1 dual, these are global sections, when fail to be independent on an R dimensional subspace on W in V, where the dimension of W is R. Okay, so for those W's where they fail to be independent, this will be exactly the ith Churn class. Okay, That's the intuitive definition of the Churn class. And it's not even intuitive here because we actually have global sections and this will have good codimension. So you solved this exercise. I know that at least some people solved it. And you know that this class looks like that. This is a Schubert class where we have I1s. I boxes, okay? So is the answer clear? So this was exercise 1 from lecture 1. Okay, so this tells us that this is 1 plus box t plus 2 boxes t square plus 3 boxes t to the third plus r boxes t to the r. It finishes there. Okay. So I'm continuing. So recall that we also said that the Chowring of the Grassmannian GRV is the polynomial ring in R variables invariant, well, and divided. You have to, kill those Young diagrams that don't fit in a rectangle. But now notice that using this isomorphism, well, this box corresponds. This box corresponds to the elementary symmetric polynomial, to the Schur polynomial corresponding to this, which is just the elementary symmetric polynomial in R variables. Okay, so using this isomorphism, Ct of U dual is, well, what is it? 1 plus E1 t plus E2 t square plus. And this is exactly the product of 1 plus xit, where we take the product from I equal 1 to r. Yeah. So the Churn roots are really the x's. So, x1 does not belong to this ring because it's not invariant polynomial, but it is a very nice interpretation that this Churn roots that don't make sense here, well, they come from the fact that our ring actually is a subring of a bigger ring, okay, where xi's make sense. And an exercise for you, and there are again a few ways to do it, is to compute Ct of Q, well, in some sense it's even maybe easier. So I mean, and again, there are a few ways to do it. It should be this. So I'm giving you the answer, but for you, your task is to prove it. Okay. Okay. So now a new task that we have. Let's do something more complicated. We will try to compute on examples the Churn polynomial of a second symmetric power of U. Okay, so S2 of U is a vector bundle, and we would like to understand its Churn classes. There is a question. Yeah, no, that's a comment. Okay, so let me. Okay, so what are the Churn roots? So Churn roots of U. Well, I can just say that they are minus x1 up to minus xr. And what I know about those things is that the elementary symmetric polynomial in the x1 up to xr, well, this is this j times as an element of the Chow ring of the Grassmannian GRV. Okay. Okay, so now will be a question for you. What are Churn roots? What are the Churn roots of S2U? You can give me some of them, you can give me all of them, but I want someone to tell me something. So Churn roots of U are minus x1 up to minus xr. What are Churn roots of S2U?
So they are all the sums minus I minus j, right?
Yes. So can you give me one example explicitly?
Minus 2x1, for example.
Minus 2x1. Exactly. That's the one I wanted to hear. So
Okay.
we allow to repeat, but there is also like -1 minus x2 and so on. Perfect.
Mhm.
Thank you very much. That was great. You see, fortune favors the bold. Okay. Now let me. Now my computer crashed again, and I'm sorry for that. I don't know what's happening actually today, but I will just proceed without that. Okay, so now let's try to actually do some computations on G24. So I will maybe start a new thing, G24. So well, we have those churn roots x1, x2. So minus x1 minus x2 are the churn roots of U. x1 plus x2 is a box, and x1 times x2 is two boxes next to each other. Okay, so what's the first churn class of S2U here? Anyone wants to have a try? So what are the churn roots here? Well, we can list them explicitly. Yeah, this is minus x1, minus x1 minus x2, minus 2x2. Okay, so what's the first churn class? What do we have to do with those things? Anyone? Oh, someone writes something. Add them. Yes, exactly. So I add minus x1 minus x1 minus x2 minus 2x2. What is this as an element of the Chowring of the Grassmannian? So I don't want to hear x's. Now I would like to see something more. Preferably Schubert classes or Young diagrams. Okay, so I will first give you a hint. Or maybe I don't have to give a hint. I see some answers. Minus 3, one box. Exactly. Minus 3 x1 plus x2, which happens to be a box. Okay. So you can see that those things, once you get used to them, they somehow become in some sense even too easy, because you just have to do very formal computations. I mean, and okay. So what about this? What about this? First with x's. What do we have to compute to get the second Churn class? What should we compute? Anyone? What we have to compute? What kind of polynomial we have to first compute in x's? So there is someone writing something and someone saying something, but the person saying something is muted. The degree 2 terms on the Churn polynomial. Yes, which would be the mixed products. Yeah, so this is called the elementary symmetric polynomial. Yeah, so we have to compute the three products: this times this times this, and this times this. Well, the good news is that I did this, and I will even give you a very nice answer. This happens to be x1 plus x2 squared. Plus 4 plus 4x1 x2, if I didn't make a mistake. Maybe someone can check me. Okay, so what does it mean? Well, x1 plus x2 is a box squared, and then we have 4 times this. Okay, but a box squared, you already know what it is. No, it's probably there is a 2 here. Let me. So what's the coefficient of x1 squared? X1 squared only appears when we do this multiplication, which probably means I'm sorry, I made an error in the notes.
Wait, that isn't it correct?
Oh, sorry.
No, wait, no, maybe it's.
So,
No, sorry. So you're right, it should be 2.
yeah,
This should be 2.
I think it's a 2. Sorry. Okay, so this gives us a 2 here. So this means that we have 2. And now, well, how do we take a product of a box if a box? It's this plus this, okay? Plus 4 times this, which gives us 2 times this plus 6 times this, okay? Now it looks better. Okay, how many else Churn classes of S2U do we have? What's the rank of S2U? Guesses are welcome. What's the rank of U? Maybe first, what's the rank of U? The universal bundle on Grassmannian G24. Don't worry if you say wrong, just say a number. It's a non-negative natural number. The rank of U on G24. Anyone? Well, over a point of the Grassmannian, it takes the subspace corresponding to that point. So what's the dimension of that subspace? U. What's the rank of U on G24? Oh, there is an answer. 2. Yeah, it's 2. Well, because it's G24. Okay. Now, if we take a second symmetric power, what will be the rank? What happens when you take the second symmetric power of something 2-dimensional? What's the rank? Rank 3, I think. Yes, I also think it's rank 3, which means we have one more Churn class to compute. Okay, C3S2U. Okay, what is this? What is this in terms of those numbers?
The product of all 3.
The product, yeah, the third elementary symmetric polynomial. Oh, okay. So this is minus 4x1 x2 x1 plus x2. Now we turn it into boxes. This is minus 4 this times a box. Yeah. Now remember that everything has to fit in the 2x2 rectangle. So this is minus for this. Okay. It wasn't that bad. So notice that now you can compute basically any Churn classes of whatever, symmetric exterior powers of universal and quotient bundle on the Grassmannian. Okay. So now a proposition, and one of the exercises is a challenge to prove it. So if E is a vector bundle with Churn roots x or A1 up to AR, then the Segre class, of E, ith Segre class, well, this is just minus 1 to the E, and then you take the elementary symmetric polynomial that I think in the complete elementary, the complete homogeneous symmetric polynomial, not the elementary. If you take the elementary, you get the Churn classes. If you get the complete homogeneous symmetric polynomial, you get the Segre classes. Okay. So again, you can express those other classes in terms of Churn roots, and there is a hint how to prove it, because you remember there is this basic equality on polynomials that defines Churn and Segre classes all together. Okay, now a remark that be very careful with sign conventions. So even Fulton, depending on the book which you take, sometimes for him, it's as for us, that the segreg class is minus the first Churn class, but sometimes they are equal. And this is just a convention on a sign. So very often people, the odd segreg classes get the different sign than the convention that I am using. Okay. Okay. So these are the tools to compute the Churn classes. Now I promised you a map from K-theory to the Chowring, and we are slowly proceeding there. The Churn classes were very useful. For that, we will need the Churn character, and now comes the definition, namely let E be a vector bundle of rank R with Churn roots x1 up to xr, x1 up to xr, and we define the Churn characters, the Churn character, define the Churn character ch of E by, this will look very, very strange, and I will spend 2 minutes describing what I mean here. Okay, so first of all, what I mean by e to xi. By e to xi, as we know from analysis, I mean this, sum from n equals 0 to infinity 1 over n factorial xi to the n. Okay, this is just a shortcut for a notation. Okay, so what does it have in degree n? Well, in degree n, it has something like 1 over n factorial x1 to the n plus xn to the n, xr to the n. Okay, this sum. Okay, notice that this is a symmetric polynomial. And one of the very nice advantages of working with Churn characters is that if you know what elementary symmetric polynomials evaluate on them, and then they evaluate to Churn classes, you can ask what's any symmetric polynomial on Churn roots. Okay, why? Because the elementary symmetric polynomials generate as an algebra the symmetric polynomials. So any symmetric polynomials can be written in terms of products and sums with coefficients of elementary symmetric polynomials. So in other words, this is some combination of products of Churn classes. Okay. Okay, so I'm going to, no, I'm not going to make a new slide because 20 is the limit, but I am still going to erase something. Let me go to the beginning and let me clear this. Okay. So, well, in principle, you could also write what this is explicitly in those Churn classes. So first you get R because you get 1 plus 1 plus 1 plus 1. Well, then you get a half of, then you get just the first Churn class because then you get x1 plus xr. And then the complicated things start. Namely, you get C1 of epsilon squared of E squared minus 2 C2 of E. Yeah. So how do you get this? Well, you have to write x1 squared plus xr squared in terms of elementary symmetric polynomials, but that's easy. You just have to take x1 plus xr squared, it's that, and subtract twice the xi times xj where I is not equal to j. And the 1/2 comes from the fact that if you expand e to x, you get 1/2. Okay, so and of course this goes forward. These formulas become worse and worse. In principle, if you want to know how to express this is called the power sum polynomial. Power sum x1 to the n plus xr to the n in terms of elementary symmetric. Well, this is amazing, but already Newton thought about it, and there is a formula due to Newton. Look at Newton formula. So I'm cheating here. Actually, this formula expresses this recursively, but still it does the trick. Okay, so why is the churn why is the just one second. Okay. So why is the churn character so nice? Maybe before that, one more example. So what happens for a line bundle? So let's say that we have, there are questions. Newton's identity, I think, if you want to Google that.
Not just that, if you just, I think it's known as Newton's identity, it should be easier to find, just that.
Okay. Yeah, probably there are like 1 million Newton's formula also in physics, and yeah, maybe Newton's identity is a better word. Add definitely elementary symmetric polynomials and power sums, and then there should be no problem. Okay, so let me do one more example. So if we have a line bundle, this is a mistake that a lot of people do. So one thing you can associate to it is the first Churn class, and this is somehow a very good representative. But notice that the Churn character on L, this is not D. Well, this is 1 plus D plus D squared divided by 2 factorial, and so on. I mean, it's a finite sum, of course. Maybe I should have also said, I cannot go back there. That all those sums, although I write them infinite, they break at some point. Yeah. So at some point, because, for example, of the grading of the Churn, this also does not go to infinity. At some point, some power of D, because Churn is graded and the finite dimensional vector space will be 0. No, actually, that's maybe not a good argument, but the good argument is that if you go beyond the dimension of the variety, you get 0. Yeah, so if you take D to dimension of the variety plus 1, that's 0. Okay, so the only thing that I want to stress here is that this is not D; it's something in D, and it has a lot of nice properties that I will list as a theorem. So if we have a exact sequence given exact sequence of vector bundles, v1, v2, v3, we have that the Churn character of v2 is the Churn character of v1 plus the Churn character of v3. Okay, so Churn polynomials multiply, Churn characters add. And one more, that if we have the Churn character of the tensor product, so these are arbitrary vector bundles, then this is just the product. Okay, so 2 facts. Okay, I have about 10 minutes, which means I will prove it actually to you. So this will be a theorem with a proof. Okay, so if we have v1, v2, v3, well, remember that we already know that Churn polynomials multiply, which means that Churn roots of v2 as a multiset, this is just a union of Churn roots of v1 and Churn roots of v3. Yeah, this is what a product of polynomial does. It takes the roots together. Okay, well, but this means that the power sum polynomial in the Churn roots, let's say nth, when n is anything, nth in Churn roots of V2, well, if this is a multiset, this means that this is just a sum of nth power sum polynomial in Churn roots of V1 and the nth power sum polynomial in Churn roots of V3. Okay? Is this clear? Any questions about that? Okay. Well, but our Churn character was exactly defined in a given degree as a power sum in Churn roots. Okay, so this is exactly saying this equality, degree by degree. Okay, because we just have a power sum polynomial, well, divided by 1 over n factorial, which doesn't matter. We just have the power sum polynomial, and this plus is exactly this plus. Okay. Okay, so now for the second point, I hope I can make it here. So let's say that xi are Churn roots of V, and yj's are Churn roots of W. Yeah, then we already know that xi plus yj, these are Churn roots of the tensor product. Yeah, this I already told you. Well, and now you can operate very formally. If you have a sum over ij e to xi plus yj, well, this is the sum over ij e to xi times e to yj. Well, but this is the same as the sum over I of e to xi times a sum over j e to yj. Okay? Well, but this is this, and this is this. This was supposed to be W. Okay? So the proofs are really easy now. Once we build a little machinery. Okay. And because of this, we have the following. Well, actually, because of those two things, we are getting. I will write it as a corollary. That the Churn character is a well-defined map from the K theory to the Chow ring. Okay. And in fact, this is a morphism of rings. Okay, and the fact that it's a morphism of rings, it's exactly this statement. And the fact that it descends to K theory, it's exactly this statement. Okay, so this is really a corollary. I'm not cheating here. Well, what is slightly harder is that actually over Q, so if we tensor over Q, this is an isomorphism. Okay. So for this reason, these rings, when we were computing on examples, the K theory and the Chow ring, they often turned to be the same. But note that the map is not so trivial between those rings, and this will be the last example with which I finish. So remember that we had Pn, and well, let me just write H, because this is really a hyperplane, a class of a hyperplane, to be C of O of 1, to be the first Churn class of O of 1. Now, what is CH of O of 1? Well, this is 1 plus h squared divided by 2 factorial plus, well, the last term here, because I know the dimension, I can write you. Okay. Now, if you look at O of -1, so you remember I told you that this is the x in the K theory, that is like the variable that makes the K theory a polynomial ring modulo xn plus 1. Well, this is just equal to minus h plus h squared divided by 2 factorial minus and so on. Well, finally, we have minus h to n divided by n factorial. Okay. Okay. So I will try to fit it here. Remember that the K theory of Pn, well, let's say over Q, this is just Q of x divided by xn plus 1. Okay. And the Chow ring of Pn, this we also said, and let's say also over Q, this is just Q of h divided by hn plus 1. Okay. And the Churn character map here, well, x is this. It sends x to this complicated thing. Okay, so it's not really an isomorphism that sends x to h, as many people think. It's more this one. Okay, and thank you very much. This is all for today. But I would like to make one thing. We can stop the recording, but I would like to make one more thing before the question and answer session.